So in this video, we're going to talk about velocity and acceleration in an uniform, in circular motion, and how forces act and happen when this kind of motion is occurring. So for instance, here we have an object that is moving in circular motion. We remember the velocity is tangent to the circle at every point, and the acceleration points towards the center, always points in that direction. You remember from previous weeks that the acceleration is v squared over r and points towards the center of the circle. So how do we use this information to talk about forces and Newton's law when it comes to circular motion? So let's look at a simple example here. We have a car that is going around a corner here, right? And then, so if there's no forces acting on the car, what's going to happen? Newton's first law, the car continues moving in that direction. Because there's friction, the friction is pushing the car towards the center of the circle, right? So this is the friction. And that friction have to be equal to mass times acceleration. And what is the acceleration? For circular motion is v squared over r. So where r is this radius here. So this here encodes most of the information that we need to solve problems in circular motion. So let's just look at that problem in a little more detail. So a car that is turning a tight corner then goes at a constant speed, right, as is shown. So the velocity vector is this guy here, and the car is moving in this direction. What is the direction of the acceleration? Well, we know the acceleration points towards the center of the circle, right? So the acceleration is v squared over r, and then we know the force is equal to mass times acceleration, and therefore we know that the force therefore has to be mv squared over r. So when we talk about circular motion, there's a few quantities that we need to define. We need to define the period. Period is the time that it takes for the particle to go one complete revolution. So that's the period. And the frequency is the number of revolutions per second. And frequency and period are related by this equation here. So the units for frequency is hertz, or 1 over second, and the units for periods are second. So if the particle goes one revolution, so the distance it covers is 2 pi r. And if you divide that by the time, that's your velocity. Velocity is equal to 2 pi r over time, or 2 pi times the frequency times r. Once you have the velocity, then you can plug here, and then you get that the acceleration is 2 pi squared over the period, or 2 pi times the frequency squared times the radius. You don't need to memorize these equations. These equations are easy to obtain from one another by using the definition of period and frequency. So let's look at an example here. Spinning a table. So you have a circular blade that has a radius of 25 centimeters, or a diameter of 25 centimeters, and a spin as 3,600 revolutions per minute. And this is per minute, so we're gonna have to transfer that to seconds. How much time is required for one revolution? How fast is one teeth at the edge moving? What is the acceleration? So let's get all that information. So we know the diameter is 0.25 meters, so the radius, which is what we need, is half of that, 0.125 meters. The frequency is given in revolutions per minute, but we need to convert this to 1 over seconds, right? So to convert that, we take 360 revolutions per minute, right? And 1 minute has 60 seconds. So then we multiply that, these two quantities here, and then we get that is 60 1/seconds. That is the frequency, 60 hertz. It goes 60 times every second. So the period, what is the period? Well, it's 1 over the frequency. That gives you this very little small number here, 0.17 seconds. The speed, well, the speed you can get as 2 pi over the, here there is a typo here, so to get the speed is 2 pi r, the distance it covers in one revolution, divided by the period, or 2 pi r times f. So here you have your frequency, so that 47 meters per second. That's a fast speed. And then the acceleration is what? Is v squared over r. You take 47 square divided by 0.125 meters. So to solve problems in circular motion, we need to use Newton's second law. So force is equal to mass times acceleration. Acceleration is v squared over r, and it points towards the center. Right, so here is a picture of how it happens, right? So we have an object that is moving, right? So the velocities are this green vector here. The acceleration are this orange vector, and you can see the net force always points towards this center. So the net force, there's always a force that is going to point towards the center of the circle and keeps the particle moving in a circle. Example here. So let's say this car goes through this bank road, and this is a circle here, right? And you're given the radius, right? So the radius is some point there. So what is the acceleration? Well, the acceleration is going to be v squared over r. So that is equal to mass times acceleration. That, if we use Newton's law, that's that is the Newton's second law applied to this problem. So now, what is this force? Well, this force in this case is the force that points towards the center of the circle, right at this point, right? So what is this force? Well, it's the net force, which is the normal force, minus gravity. The net force here, right, the addition of these two have to be equal to mass times v squared over r. So that's how we work with this type of problems. So let's look at another problem here, right? So we have a car that is going through a curve, right? So then what keeps the car going in this circle? Well, there's gotta be a force that points towards the center. That force is the friction, and the friction has to be equal to mass times acceleration. So this is how we are going to solve this type of problems too, by using these two equations, this equation here. So here is the problem. Let's just look at these two examples to make sure we understand how this works. What is the maximum speed that a car that is 1,500 kilograms can have to make a turn around a curve that is the radius of 20 meters? This is a level road and there's no sleeping. So this is the problem. So we know the mass, we know the radius, we know the friction, the static friction coefficient, right? So the car is not going to be moving in this direction, it's moving in this direction. So in this direction, there's only static friction coefficient. In this direction, there is rolling coefficient, there is rolling friction. So free body diagram for the car, we have normal force, weight, and friction, right? So the friction points in this direction, right? It keeps the car in the circle. So the net force is then equal to the friction. So now we can use Newton's second law. Net force, which is friction, is equal to mass times acceleration. And then we can solve for the velocity, which is what we want to find. That happens when the friction is maximum. Right at that point, when we have maximum friction, is when we have the maximum velocity. So maximum friction happens when you get the friction coefficient times the normal, right? So that is mu s times mg. So then we can write that mu s times mg is equal to n v squared over r, or v squared is equal to mu s gr. And this is the equation, the final equation. When we put the numbers there, we see that this is 14 meters per second. Does that make sense? Well, for this type of curve, for that friction coefficient, if you're going at 14 meters per second, which is roughly 30 miles per hour, you will stay on the curve. So you can change these and then add a banking. So you can have a bank curve. So in that case, then now the centripetal force is going to be given by this component of the normal force. That's what is going to keep the car in place. So let's look at this example. So this is a racetrack. The radius is 70 meters and the banking is 15 degrees. What is the maximum the maximum speed this car can take when it takes this curve? So let's look at the free body diagram. So what are the forces? We have normal force and we have weight, and we are neglecting friction here, but friction, we can add friction later. So then we have two equations, right? So we have an equation for the y-axis and an equation for the x-axis. In the equation for the y-axis, we have the weight minus this component of the normal force, which is n cosine theta, that have to be equal to 0. And in the x-axis, we have this component of the normal force, that is the net force, and that have to be equal to mass times acceleration. And what is the acceleration? V squared over r. So now we can go ahead and solve for the normal force. From these two equations, I can take this from here and put it here. So if I did that, then I get the normal force is y divided by the cosine theta. Putting it back in the top equation, we get mg tangent theta, this is a tangent, right, is equal to mv squared over r, and then we can solve for the velocity, and we get that is 40 meters per second, which is the same speed that we got before. So this banking with 15 degrees is the same as the centripetal force that you get from the friction coefficient that we had before. You sometimes heard about centrifugal force. What is centrifugal force? That is an apparent force. It's not a real force, and it's the feeling that you have because of Newton's first law. You're trying to keep going in this direction, and the car is pushing you in that way. So you feel as if there was a force that is pushing you in the other direction, and that means that this is an apparent force. It's not a real force. Another case where apparent forces appear in circular motion is when you go on roller coasters. Here you're going to feel heavier and heavier because of the mv squared over r term, and here the same, you're going to feel a little lighter, right, because of this term too. All right, thank you very much.